Welcome to our deep dive into typecasting in C++. In this video, we'll unravel the concept of typecasting, which is the process of converting one data type into another within your C++ programs. Whether you're a beginner or looking to refresh your knowledge, understanding typecasting is essential for writing efficient and error-free code. We'll explore both automatic and manual conversions, see real code examples, and discuss best practices. By the end, you'll be equipped to handle data type conversions confidently and avoid common pitfalls. Let's get started by understanding what typecasting really means in the context of C++ programming. Typecasting, also known as type conversion, refers to changing a variable from one data type to another. In C++, this is a fundamental concept that allows you to manipulate data more flexibly. Sometimes, the compiler handles the conversion automatically, while other times, you as the programmer need to specify exactly how the conversion should occur. Typecasting ensures that operations between different data types are performed correctly, and it helps prevent errors that might arise from incompatible types. Next, let's look at the two main types of typecasting in C++, implicit and explicit. Implicit typecasting, or implicit type conversion, happens automatically in C++. The compiler upgrades or converts a variable to a compatible, usually larger data type without any intervention from the programmer. For example, if you add an integer and a float, the integer is automatically converted to a float before the operation. This process is safe as long as the conversion is from a smaller to a larger data type, such as from int to float or float to double. However, converting from a larger to a smaller type can lead to data loss or warnings. Let's see how implicit typecasting works in practice. Consider this simple C++ program. We declare a short variable with a value of 200 and then assign it to an int variable while the compiler automatically converts the short to an int. When we print both variables, they both display 200, showing that the conversion was seamless. Additionally, adding an int and a char, like 20 plus, results in an int value, demonstrating how characters are implicitly cast to their ASCII integer values. Similarly, adding an int and a character to a float variable results in a float, showing how implicit casting works across different types. The output of our previous example confirms the automatic conversions. Both x and y display 200. The result of 20 plus is 117, and the float value after adding num and a is 85. This demonstrates how C++ handles implicit typecasting behind the scenes, ensuring that operations between compatible types proceed smoothly. However, always remember that implicit casting should go from a lower to a higher data type to avoid precision loss or compiler warnings. Explicit typecasting, also called manual typecasting, is when the programmer decides to convert a variable from one type to another. This is done using a cast operator, and it gives you full control over how and when the conversion happens. Unlike implicit casting, explicit casting can be used to both upgrade and downgrade data types, regardless of compatibility. This is especially useful when you want to force a conversion, such as truncating a floating point number to an integer. Let's look at the syntax and see how explicit typecasting is performed in C++. The syntax for explicit typecasting in C++ is straightforward. You simply place the desired type in parentheses before the value or expression you want to convert. For example, to convert a floating point number 4.534 to an integer, you write int 4.534. This truncates the decimal part and assigns only the integer value to your variable. Explicit casting is powerful, but you must use it carefully to avoid unintended data loss or logic errors. Let's see a practical example of explicit typecasting in action. In this example, we declare two integer variables a and b with values 21 and 5. When we divide it by b without casting, the result is 4, since integer division truncates the decimal. However, by explicitly casting one operand to float, as in float 21/5, the result becomes 4.2, preserving the decimal part. This shows how explicit casting can help you get the desired result, especially when working with mixed data types. Let's consider another example where we calculate the area of a rectangle. The length and breadth are stored as double values. By casting the double to int, we get an area value that is truncated to an integer. By casting to float, we retain the decimal precision. This demonstrates how explicit casting allows you to choose the level of precision you need for your calculations, making your programs more flexible and accurate. We input the length as 57.3456 and the breadth as 12.9874. Casting to int gives an area of 740, while casting to float results in 744.77. This clear difference highlights the importance of choosing the right typecasting method based on your program's requirements. Always consider whether you need to preserve decimal values or if truncation is acceptable for your application. C++ provides 4 specialized cast operators for more advanced type conversion: static cast, dynamic cast, const cast, and reinterpret cast. Each serves a unique purpose and is used in different scenarios. These operators give you greater control and safety when converting between types, especially when dealing with pointers, references, or class hierarchies. In the next few scenes, we'll explore each cast operator in detail, starting with static cast. Static cast operator is used for compile-time conversions between compatible types. It can perform all conversions that are allowed implicitly, and it's also used for casting pointers within a class hierarchy, such as from a derived class to a base class or vice versa. However, static cast does not check the validity of the conversion at runtime, so it's the programmer's responsibility to ensure the cast is safe. Let's see how static cast works with a practical example. In this example, we declare a double variable L and assign it the value of 2.5 multiplied by 3.5 and 4.5, resulting in 39.375. Using static cast int L, we convert the double to an integer, which truncates the decimal part and stores 39 in the integer variable tot. This demonstrates how static cast can be used for safe, compile-time conversions between numeric types. Static cast is also useful for casting pointers between related classes. For example, you can cast a pointer from a derived class to a base class, or vice versa, as long as the classes are related. However, casting from base to derived should be done with caution, as static cast does not check the validity at runtime. This is especially important in complex class hierarchies, where incorrect casting can lead to undefined behavior. Dynamic cast is a runtime cast operator used mainly with pointers and references to classes. It checks the validity of the cast at runtime, making it safer for downcasting in polymorphic class hierarchies. If the cast is invalid, dynamic cast returns a null pointer, preventing undefined behavior. This makes dynamic cast ideal for situations where you need to ensure the object's actual type before performing the conversion. Let's look at a code example using dynamic cast. We have a base class and a derived class. When we try to cast a pointer from the base class to the derived class using dynamic cast, the cast will only succeed if the base class is polymorphic, meaning it has at least one virtual function. If the cast is invalid, dynamic cast returns a null pointer, allowing you to check and handle the error safely. This is especially useful in large projects with complex class hierarchies. In our example, when we cast a parent pointer to a derived pointer using dynamic cast, the cast succeeds if the object is actually of the derived type. The output confirms that dynamic casting is done successfully. If the cast fails, the pointer is null, and you can handle the error gracefully. This runtime safety feature makes dynamic cast a powerful tool for managing complex object hierarchies in C++. Reinterpret cast is used for low-level casting between unrelated pointer types. It allows you to convert any pointer type to any other pointer type, or even to an integer type and back. However, reinterpret cast does not check for type safety, so it should be used with extreme caution. This operator is mainly used in systems programming or when interfacing with hardware, where you need to manipulate raw memory addresses. In this example, we declare an integer pointer and use reinterpret cast to convert it to character pointer. When we print the values, we see the memory address and the character representation of the value stored at that address. This demonstrates how reinterpret cast can be used to interpret the same memory location in different ways. However, misuse of reinterpret cast can lead to undefined behavior, so always use it carefully. The output of our reinterpret cast example shows the integer pointer's address, the character pointer's value, and the dereference values. For instance, the integer value 65 is interpreted as the character A. This flexibility is powerful but risky, so reinterpret cast should only be used when absolutely necessary and when you fully understand the implications. Const cast is used to add or remove the const qualifier from a variable. This is useful when you need to pass a const variable to a function that expects a non-const parameter, or when you want to modify a value that was originally declared as const. However, modifying a truly constant value can lead to undefined behavior, so use const cast only when you're certain it's safe to do so. In this example, we declare a const integer and obtain its address. Using const cast, we remove the constness and pass the pointer to a function that multiplies the value by 10. The output shows the modified value, demonstrating how const cast can be used to manipulate const variables when necessary. Remember, only use const cast when you're sure the original value can be safely modified. Recap: C++ offers 4 specialized cast operators: static cast for compile-time conversions, dynamic cast for safe runtime conversions in class hierarchies, reinterpretcast for low-level pointer manipulation, and constcast for changing const qualifiers. Each operator serves a specific purpose and should be used appropriately to ensure type safety and program correctness. Understanding when and how to use each cast operator is crucial for advanced C++ programming. Now let's shift gears and talk about exception handling in C++. Exceptions are problems that arise during program execution, such as dividing by zero or accessing invalid memory. Exception handling provides a structured way to detect and respond to these errors, making your programs more robust and reliable. In C++, exception handling is built around three keywords: try, catch, and throw. Let's explore how these work together. Exception is an unexpected event or error that occurs during the execution of a program. For example, trying to divide a number by zero or accessing an array out of bounds can trigger exceptions. Handling exceptions properly allows your program to recover gracefully from errors, rather than crashing or producing incorrect results. In C++, exceptions are managed using the try, catch, and throw keywords. The try block is used to wrap code that might generate an exception. This is known as protected code. If an exception occurs within the try block, control is transferred to the corresponding catch block. The try block is essential for isolating risky operations and preparing your program to handle errors gracefully. The catch block follows the try block and is used to handle exceptions that are thrown. You can have multiple catch blocks to handle different types of exceptions. When an exception is thrown, the catch block that matches the exception type is executed, allowing you to respond appropriately to different error conditions. The throw keyword is used to signal that an exception has occurred. When a problem is detected in your code, you can use throw to pass an exception object to the nearest catch block. This mechanism allows you to separate error detection from error handling, making your code cleaner and more maintainable. The basic syntax for exception handling in C++ involves wrapping your risky code inside a try block, followed by one or more catch blocks to handle specific exceptions. For example, try, protected code, catch exception type E, / handle exception. This structure allows you to isolate error-prone code and provide targeted responses to different types of exceptions. In summary, mastering typecasting and exception handling in C++ is essential for writing robust, efficient, and maintainable code. Always choose the appropriate typecasting method for your needs and use cast operators responsibly to avoid errors. Implement exception handling to make your programs resilient to unexpected events. By following these best practices, you'll be well equipped to tackle complex programming challenges in C++. Thanks for watching and keep coding.